Hello everyone. Today's topic is distance protection of transmission lines, and in this topic we'll cover why overcurrent relays are not suitable for EHV lines, the types of distance relays, their comparison, complete protection of our transmission line, and a three-step distance protection. So overcurrent relays are not suitable because their reach varies with the magnitude of fault current, the fault type, as well as with the source impedance. So for this network we can see that if the line section AB is to be protected and three faults, let us say LG, double LG and three-phase fault are considered, the reach of the relay placed here, the reach of the relay varies with the type of fault. For a line to ground fault, the reach is B1. For double line to ground fault, the reach is still B. And for three-phase fault, the reach extends from A to B2. And this is not desirable for any longer line, that is EHV lines. This may be tolerated for shorter lines. So this can't be accepted. Now the overcurrent relays also vary. The reach of the relay also varies with the source impedance. Let us see. These three are source impedances as we saw in the previous slide. For the three faults, the source impedances will vary and the reach of the relay will vary similarly. So it is not desirable, and hence we adopt a distance relay or impedance relay for the same, so that this shortcoming can be overcome. Now for the same system where AB is the line section to be protected, this is the relay, and the reach of the relay we are assuming AB. So we can consider three faults at F1, F2 and F3. F1 is the fault between A and B, so it is an internal fault. This is an external fault. So for external fault, since the impedance seen by the relay is less than the set impedance of the relay, which sets the reach of the relay. So impedance seen is greater, that is why the relay will not operate, it will restrain. For the internal fault, the impedance seen by the relay is less than Z set, so this relay will operate, and for a fault occurring at point B, it is on the verge of operation. Now the relay characteristic can be shown by this VI characteristic and RX characteristic, and in the previous slide we saw the equations in terms of voltage current. Now we can see the equation in terms of impedance. This can be modified to this equation where ZR is the Z seen and Z set is the impedance set for the relay to trip during faults. Now this is the VI characteristic. You can see the slope of VI characteristic is the impedance set for the relay to trip. On RX characteristic, this can be drawn as a circle. The impedance set for the relay to operate can be taken as the radius, and it will draw a circle. So the inside of the circle will give you the trip region and outside is restrained. The relay will not operate if any fault point exists, that is for fault point F3, it will not operate, it will restrain. We can see the three fault points F1, F2, F3 in the previous slide here. So the effect of arc resistance can be shown on the impedance relay by means of this formula, Warrington formula, where S is the spark over distance, velocity of dielectric, this is the time, and current. This arc resistance comes into effect whenever the contacts of a circuit breaker separate in order to interrupt a fault current. So we can say if this is the line fault characteristic, the arc impedance will add into it and the total impedance will increase. With respect to this O point, the total impedance seen by the relay will increase and hence relay will not operate. So this causes underreaching of a relay, as we'll see in the later slides. This impedance relay torque equation can be expressed by this, in which four constants are there: K1, K2, K3 and K4. Three constants are due to current, voltage, and this is the directional element which is energized by voltage as well as current. And the fourth element, that is the K4, is the torque due to the spring. So impedance relay can be of three types: simple impedance relay, reactance and Mho relay. We'll see one by one. Simple impedance relay, the torque equation will be given by current and voltage, where this is the current is the operating quantity, voltage will be the restraining quantity. And it will give an equation. If the impedance seen by the relay is less than the set impedance, then the relay will trip, else it will restrain. So the balanced beam structure for this simple impedance relay can be shown by this, where voltage coil gives you the restraining quantity. This is the operating quantity. If the operating quantity exceeds, the balanced beam will deflect towards it and the trip circuit is operated. Now the simple impedance relay during normal load flow is stable during normal load flow. Let us say this is this Rx on this Rx plane. This circle gives the operating characteristic and the straight dotted line gives you the normal load flow characteristic. So whenever during fault any point coincides with normal load flow characteristic, the relay will operate. So during normal load flow, line fault characteristic will not give you any point on normal load flow curve. So there is no chance that the simple impedance relay will operate. The effect of arc resistance on a simple impedance relay can be explained by this. Let us say if a fault occurs on point C, the impedance seen by the relay will not be AC, it will be AC plus CR. So it will be AR, that is the impedance seen by relay increases. Now this is inside the trip region. Let us see if a fault occurs on point B. If a fault occurs on point B, the fault will include the arc resistance and this arc resistance will be included here, increasing the impedance to a point somewhere outside this circle and it will come into the restraining region. That means the relay will not operate. This is known as the underreaching of relay. Relay underreaches because of arc resistance. Now let us see the directional property. Simple impedance relay is not directional because it is a circle which encompasses all the four quadrants. So let us say if we have to protect a line section AB, the impedance set here is Z set. Now, if a fault occurs between AB and the current flow is in the forward direction AB, the relay will operate. But since the relay occupies the third quadrant also, so if a fault occurs between AC, where we are assuming that AB and AC are of equal lengths, then the relay will also operate for the fault occurring between the line section AC. That is, it will operate during the forward faults as well as reverse faults and hence it is not directional. Now the power swings have effect on a simple impedance relay since its area is larger and occupies all the four quadrants. The more the area of the characteristic on the Rx plane, the more it is vulnerable to the mal-operation due to power swings because during a power swing, the voltage and current vary heavily and hence they can come into the locus of power swings, that is at the point C. Point C is known as the electrical center because it coincides the line fault characteristic as well as the locus of power swing. So the probability of uh, the system falling at point C, that is the electrical center, is more during power swings and hence simple impedance relay is not immune to power swings. It will operate during power swings. Now see, let us see all these things in terms of reactance relay. The torque equation will be modified where we take two quantities, current and VR IR cos theta minus tau. This is the directional element of the torque equation. Okay, it does not define whether the relay will be directional or not. So we take two quantities where IR is the operating quantity and VR IR cos theta minus tau is the restraining quantity. So if this operating quantity is greater than the restraining one, this relay will operate. This equation can be modified to this one where we can see that this tau maximum torque angle can be made to be 90 and if it is made to be 90, the equation modifies to reactance curve or reactance equation. That is, if the reactance seen by the relay is less than the reactance set for the relay, then it will trip, otherwise it will restrain. So let us see its construction, four-pole construction. We can make the maximum torque angle to be 90, that is tau is 90, by keeping resistance very high than the reactance of this restraining coil and the other is the operating coil. Here we have to keep in mind that the reactance relay construction is very light. It is very light in weight. So torque to weight ratio is very high. Hence it is very sensitive and it operates very quickly. So we need to keep this point into mind. Reactance relay normal load flow characteristic coincide this curve, its operating characteristics and hence it will operate. The operating characteristic of reactance relay will consist of a line parallel to the R axis where xn is set impedance and this will be equal to xn. So if the normal load flow characteristic coincide this region the relay will operate, and it is coinciding, so the relay operates. Similarly, we can see the effect of arc resistance. Now the arc resistance will be, if this is the line fault characteristic, the arc resistance will add. Let us say AB is the reactance or impedance seen by the relay. Now resistance, fault resistance BC will add into it. So the total reactance seen by the reactance relay, if it is applied into the system, is AC. And hence we can see the impedance is not varying. That is, the reactance is not varying. Reactance seen by the relay is same, and hence its reach is not varying and its operation is not varying due to the effect of arc resistance. This is a very positive point which will count for this reactance relay to be used in conjunction with other relays. Now we can see the effect of direction. See, if there is any fault occurring in forward or reverse direction, the relay characteristic which are drawn above R axis or X axis can be drawn below X axis also, and these faults occurring either in the forward or backward direction will operate the relay. Hence it doesn't possess any directional property. It operates both in forward as well as reverse directions. So power swings, during power swings, the voltage and currents heavily vary. So it operates during power swing. During power swing, the locus of power swing, let us say it is this, and the fault characteristic is given by this line, where ZSB and ZSA add and gives the modified characteristic during power swings, this one. So during power swings, this happens with the reactance relay, that during power swings, the operation of the system will fall at point C, and hence the relay will operate. As ZSB approaches this center C, electrical center, the relay will operate, and this is an undesirable operation. We don't want this. Now see the reactance the characteristic of Mho relay. The torque equation is given by this, where we have to take only two components here. We have to take a directional component and a voltage component, and we make this component as the operating quantity and voltage as the restraining quantity. So this operating quantity, if it exceeds the restraining quantity, the relay will operate. We can modify the equation, and equation becomes this, that is, if the impedance seen by the relay is less than impedance Z, that is Zn cos theta minus tau, then it will trip, otherwise no. This is the characteristic. Now Zr, this is Zr, this is Zn. Theta is the angle between R and Zr, and tau is the angle between R and Zn. So this angle becomes theta minus tau, and Zn cos theta minus tau is AB. So if the impedance seen is less than AB, then the relay will operate, otherwise it will not operate. Induction cup construction of the Mho relay, it is shown here, where R and C can be used to set the desired value of maximum torque angle, and its construction is as shown. Now the characteristic can be shown here. For normal load, during normal load, the probability of a fault point falling on normal load characteristic is very less, and it will not operate. Similarly, for effect of, if we see the effect of arc resistance, the relay underreaches like simple impedance relay, but underreach is lesser than simple impedance relay. Let us say the impedance arc resistance is BC, so the total impedance seen will be OC, and hence the underreach, the impedance set for the relay is OA, so the underreach will be given by AB by OA into 100%. So there is an underreach due to the effect of arc resistance in Mho relay, but the percentage is quite less as compared to simple impedance relay. Now the simple impedance relay, we have seen it is not directional. Reactance relay is also not directional, but a Mho relay is a directional relay, since it operates only in this direction. This is the trip region, and outside of this circle is restraining region. So it only operates for this region. So it is a directional relay. During power swings, it is less immune, but let us say if there is a large power swing and the impedance seen by the system or the relay approaches the electrical center, that is point C. Electrical center is the point where the locus of power swing as well as the line fault characteristic coincide. So if it coincides, the relay will operate. And we don't want such operations, so we can use some relays known as blinders which prevent such operation. Now we can see the comparison of all three relays. The operating quantity For two relays, these two relays is current, and here it is the directional element V into I cos theta minus tau. The restraining quantity is voltage for simple impedance relay and Mho relay. Here it is the directional quantity. Now there is no directional property for simple impedance and reactance relay. Only Mho relay is directional. On load, only reactance relay trips. On load performance is good for simple impedance relay and Mho relay. They don't trip. Fault resistance, the effect of the fault resistance, that is the arc resistance, is observed on simple impedance relay as well as Mho relay. The reach of the relay remains unaffected in reactance relay. The area occupied on the Rx plane is moderate for simple impedance relay, however it is very large for reactance relay, and it is the smallest for Mho relay. Now the power swings effect causes the relay, simple impedance relay and reactance relay to operate. However, Mho relay doesn't operate. We can see the complete protection of a transmission line using distance relays. You can refer to the book I have referred, that is by E.G. Pathankar and S.R. Bhide, Fundamentals of Power System Protection. It gives you this circuit, and you can refer for different types of faults. All types of shunt faults are derived there, and we can see for detecting all these faults we need only 6 relays, where the inputs we need are the line voltages VAB, VBC, VCA, and the phase voltages VA, VB, VC, whereas the input currents will be the line currents IA minus IB, IB minus IC, IC minus IA, and the phase currents plus some restraining quantity IA plus K I R E S. This is the residual current. Now this covers all the 10 shunt faults. If we connect the system and we measure all these quantities by means of CT and PTs by connecting them here like this, we can cover all the 10 shunt faults and we can secure the system for all these faults. Now distance relays have some inaccurate reach because of inaccurate CT-PT ratios. There is an ambiguity in line parameters also, and variation of line parameters with atmospheric conditions. Also DC offset current is also there in fault currents, which causes inaccurate reach. Transient response of CVT also causes inaccurate reach of distance relays. So only one distance relay is not sufficient. We have to use a 3-step distance protection of transmission line. How? We can see we have to give 3 steps in a particular section of a transmission line. The first step, the relay reach will be set to 80 to 90% of the line length. It is instantaneous. The second step covers the 10% of the remaining section of line here, and 50% of the next line section. This line section should be shortest. It has a greater operating time than the operating time of the first step. That is, first operating time of the first step plus circuit breaker operating time and relay over travel time. The third step will include the 100% primary protection of the considered line plus 100% of backup protection of the longest adjoining line, or plus 10 to 20% extra, that is some one more adjoining line. So the operating time will be greater for the third step. Now we can see the construction here. If this is the system where the line to be protected is line section AB. Now in this system, let us say BD is the shortest line section and BC is the longest line section. We need these two sections for step 2 and step 3. So we will provide the step 1 protection here by means of this relay, the step 2 protection for the shortest adjoining line section by means of this relay here, and the step 3 protection by means of this relay. So step 3 protection will give you the protection of line AB plus protection of line BC plus 10 to 20% extra. That means the reach of the relay will be Z3. The first step will give you the protection 80 to 90% of AB, that is the reach will be Z1. The second step will give you 10% of the remaining line section, that is this section, plus 50% of the shortest line section. That means the reach of relay will be up till here, and if we extend it to longest line section, it will be till Z2. So the reach of the relay for the second step is till here. If we take it for the longest line section, there is a problem of selectivity, the relay will not operate. And the characteristic, Rx characteristic for the same 3-step distance protection can be shown here, where Z1, Z2 and Z3 will give you 3 curves with greater time and with greater distance to operate. So this completes the distance protection of transmission lines. Thank you for watching, and if you have any doubts or if you want more such videos, you can write the question as well as the topic in the comment section. Thank you so much.